Howdy! We are MXET 300 Group 6 of the Fall 2024 semester, and this is our final project proposal video.
Our final project will utilize a Scuttle drivetrain in tandem with a custom-designed Ackerman steering system in order to replicate the autonomous control of a self-driving vehicle. A 3D printed servo-actuated Ackerman steering system will be attached to the front of the Scuttle and will also utilize a custom LiDAR and camera mounting system. The software programmed into the Scuttle will utilize the Ackerman steering equations to convert steering angle values of the front wheels into the necessary wheel speeds for the back, which will be on the Scuttle drivetrain. The LiDAR reader will be used to dictate the controlled driving of the Scuttle within a 3D printed lane, and computer vision will be used to detect the color of a small scale traffic light, which will be either red or green, and the Scuttle will execute the behavior of the stoplight as any legally operating vehicle would. And lastly, the LiDAR detector will also be used to prevent the vehicle from colliding with any stationary or moving objects.
To achieve a robot that simulates a self-driving vehicle, the following technicalities will need to be engineered and implemented into our Scuttle. On the software side of things, since the differential is not being used, a script will calculate and implement the rear wheel speeds needed to perform turns using an Ackerman steering mechanism. A computer vision library will be utilized to detect the red and green lights from the 3D printed stoplight, a script for the Ackerman steering mechanism / servo control, and a script for LiDAR object detection and avoidance.
On the mechanical side, a steering mechanism will be modeled and 3D printed for linking the front steering wheels, as well as we will model and 3D print the front wheel assembly and create a custom road and obstacles for the testing.
So our robot is going to be using two separately steering front wheels using the Ackerman steering mechanism. The linkage will provide correct turning radius for each side of the robot, so that way no wheel is going to slip. This is nice because it allows us to effectively treat this as two bicycle Ackerman steering equations instead of just a single front axle. The custom LiDAR and camera mount holds the LiDAR as close as possible to the ground, so our 3D printed road doesn't need to be too high, so we save material there. We're going to be using a single servo to control the steering of both the front wheels with its own respective linkage, and the front wheel pods are also going to be 3D printed. So the project timeline has a pretty aggressive mechanical aspect to it, so we are going to be going for about 1 week total of CAD and manufacturing directly into the Ackerman steering into virtual, which will be due on the 5th of November. Then we're going to spend a lot of time to make sure the robot executes its required behaviors correctly. That's going to be the lane keeping and obstacle avoidance on the LiDAR side and the stop line behavior on the CV side. And then we have a week plus of testing tuning margins so we can ensure the project operates exactly how we want it to. So I'm going to be in charge of the project management, so I'll oversee everyone's task completion in our Microsoft Planner, as well as the mechanical aspects and manufacturing of our 3D printed components.
I will be managing the Ackerman steering virtual differential for the coding end of things and the stoplight CV and programming. Roberto will also be helping me with those assignments.
As for me, Kyler and I will work on lane keep and obstacle avoidance, and all of us are working on the project proposal and the tuning and testing.
I'll also be working alongside Ryan on the robot component manufacturing.
The Scuttle demo for our project will be expected to avoid any stationary and moving obstacles placed alongside the path of the robot using LiDAR. It does not say moving here, but it should. Drive centered in the defined path using the LiDAR. The path will be defined by those 3D printed lanes. Detect the 3D printed boundaries placed around the robot used to indicate a lane. Detect the color of an artificial stoplight with a color sensor and react accordingly. Once again, if it is red, it will stop. If it is green, it will proceed. Utilize Ackerman steering as the Scuttle drivetrain simulates the effects of a differential gearbox. And it will be rear wheel drive with a front wheel steering as described by the Ackerman steering system.
All right.
Thank you.
Thank you so much.